So for our first example, it's basically just asking us to evaluate this indefinite integral. So we do the same thing that we did back in chapter 5, except that we don't need to subtract anything and we just add a plus c at the end. Well, since we finally made it to chapter 6, we no longer have to think so hard about what the antiderivative is. We can use these integral formulas, which I'm going to get to all of these in a second. I'm going to use this first one, though, because this is the one that deals with powers of x. Okay, so this is telling me that if I have x to a power, the antiderivative of that would be that same x risen to a power that is 1 greater than this power. So add 1 to the power, and then just divide by whatever that number is, by whatever that new power is. Okay, that's pretty much what the rule is. Okay, now let's go ahead and do this the way we were doing this before, where we would basically go, we would just have to think backwards. We would ask ourselves, what function would I have to have that if I took the derivative of it would leave me with negative x to the negative 3? So this is how we did this problem before. We would say, well, I know that the original power had to be 1 greater than that because I had to subtract 1 from it to get negative 3. So my original function would have had to be x to the negative 2. But there must have been something here. I don't know what that something is. There must have been something times that, so that when I take the derivative, I would have negative 2 times that something of x to the negative 3, because I would have to subtract that power, subtract 1 from that power. And then I notice in this function here, there's a negative sign. So whatever this was, negative 2 times this number had to be negative 1. So that means this number had to be 1/2. And that's how we kind of figured out the big fat question mark. Okay, that has to be 1/2. In order for negative 2 times the mystery number to be negative 1, the mystery number would have to be 1/2, since negative 2 times 1/2 equals negative 1. Okay, so that's kind of how we did this. We sort of were like, all right, I need to think backwards and sort of guess and check and do some erasing and blah, 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 blah. Okay, so far I've got the first part. I've got 1/2 x to the negative 2. And if you're not sure, you can check yourself. You can go, okay, if that's capital F, then the derivative of that would be negative 2 times the 1/2 times x to the negative 3, and then you would see that the negative 2 and the 2 cancel, but you're still left with a negative. So you'd have negative 1 x to the negative 3rd, which is what I had here, which means I did it right. So that's the guess and check method, which, you know what, never fails. When in doubt, you forget a formula, you can do guess and check. Okay, so I got the first part down. Whoopsies. Then I need to figure out the antiderivative of this guy, of the x. So then we'd have to go through the whole process all over again and blah, 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 blah. Or, now that we have made it successfully to chapter 6, we can start taking advantage of this formula. Let's look and see how this would have worked in the last one I just did. In the last one I just did, I have x to the negative 3. So if I follow this formula, I would have to add 1 to negative 3, which would get me negative 2. And then I would have to divide by the negative 2. So I'd have x to the negative 2 divided by negative 2. Or you could think of that as negative 1/2 x to the negative 2. And then I would have just taken my answer and multiplied it by negative 1. That's the constant multiple rule that we learned back in chapter 5. You can just multiply the constant, which in this case is negative 1, by the antiderivative, and then that would have, those negatives would have canceled, and bada boom, bada bang, I would have had this. So it does kind of save us some of all that guessing and checking and erasing and all that stuff. So I'm going to go ahead and use the same formula here. So I've got x to the first. So my n in this case would be 1. So x to the first. So I'm going to add 1 plus 1 is 2. X squared divided by 2. Or I could think of that as 1/2 x squared. I like writing it that way better. I don't know. I'm just weird like that. They mean the same thing, and there really is no one right way over the other. It's just me being me. Okay, so we have 1/2 x squared, or x squared over 2. Okay, then this one has no x, so you could think of that as x to the 0. Right? Think of that x to the 0. So I have x to the first divided by 1, which is just x. And then I multiply that x by -1. I get negative x. Almost done, because we found the antiderivative. This is what you don't want to forget, and it's in all of the formulas here, 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 so on. Plus c, because there's no limits of integration. I'm not minusing anything out. That is my final answer. Okay, so as you saw, I kind of cheated for the second and third part. Well, it's not really cheating, but I basically used this formula to find the antiderivative because it saves a lot of time. Because after doing a lot of these over and over again, you're going to start recognizing that this is really all you're doing. And if you can turn something you recognize, a pattern you recognize, into a formula, it saves time eventually, if you can remember the formula. So what I wanted to do is basically find the derivative of this to see, in fact, that x to the n is the derivative of this, making this the antiderivative of x to the n. So if I was going to go ahead and find the derivative of x to the n plus 1 over n plus 1 plus c, first I would do the derivative of x to the n plus 1 over n plus 1, and then I would do the derivative of c, because that's how we do derivatives. We split it up over the sum and do them separately and then add them together. Well, the derivative of c, that's just 0, because derivative of any constant is 0. And then the derivative of x to the n plus 1 over n plus 1, I would use the power rule. And I would say, okay, the power rule says to bring the power in front and subtract 1 from it. So I would have n plus 1 times x to the n, because I would subtract 1 from n plus 1. And then I just leave whatever constant is there. So this is like 1 over n plus 1. I just leave that constant in the equation. That's the constant multiple rule. And if you notice, these cancel out. And you're left with x to the n. So this is, in fact, the derivative of this, x to the n plus 1 over n plus 1 plus c, which makes this the antiderivative of x to the n. And notice this has been generalized for all n. N is any real number. Well, actually, sorry, close. Any real number except -1. So if you can remember this formula, this is like about half of the antiderivatives you're ever going to do. You're going to be using this formula. But notice this. It doesn't work when n is -1. And the reason for that is because what happens when you add 1 to -1? You get 0. When you add 1 to -1, you get 0. And I would be dividing by a 0, and that cannot ever happen. Also, because as it turns out, back in 3-9 of our book, the derivative of ln of x was equal to 1 over x. That means the antiderivative of 1 over x is going to have to be ln of x. So that is the exception for this power rule. So the power rule works for all real numbers n except -1. If you do end up having a 1 over x or x to the -1, the antiderivative of that would be ln of x, because when I would do the derivative of ln of x, it always equaled 1 over x. And so now we're just going in reverse. Also, they went ahead and put the x in absolute value because we have to make sure that whatever we're plugging into a natural log is positive. And see, when you're going this way, I don't have to put the absolute value because that's already the restricted domain. And so this is already restricted to positive x's. But when you're going backwards and you're just given this function, it's not necessarily restricted to positive x's. So when you go to turn it into the log, you have to put the absolute value around the x to make sure that you're only plugging positives into the natural log. And if you don't believe me, try plugging a negative into your natural log in your calculator and see what it tells you. Okay? Okay, so when we're going backwards, remember to put the x in absolute value. All right, moving right along to the exponential formula. Now here they put a k in there because they wanted you to see sort of what happens when you have e to a constant times x. So k is just a constant. It's just a number. It's not a variable by any means. Well, let's see what would happen if I took the derivative of e to the kx just by itself. Let's see what would happen if I did that. Well, I would have to use chain rule, which would first say, okay, take the derivative of e to u, e to the u, or the blop. Derivative of e to the blop would just be e to the blop times the derivative of the blop times k. So because there should be a k there, when you take the derivative of e to the kx, you end up with k e to the kx. So in order for the derivative to just be regular e to the kx, you've got to divide out that k. That's the way that it would go away, and you would just have e to the kx. So that's why they'd have a dividing by k here. Because if I came back over here and said, okay, now I want to do the derivative of e to the kx over k, well, that would be e to the kx over k times k. And we would have the canceling that we needed in order for the derivative to just be e to the kx. That is why the antiderivative is dividing by k, to multiply out the k that would be there when we took the derivative using chain rule. So basically, it's a lot like derivatives. You know, derivative of e to the kx is e to the kx times k. Antiderivative of e to the kx is e to the kx divided by k. So you're just dividing instead of multiplying. Same idea is at work here. Because if I were to find the derivative of negative cosine of kx, I'm going to ignore that for just a second. I would go, okay, this would be chain rule again. Because it's cosine of blop. And this right here is my blop. So I would go, okay, I would have the constant, so it's just negative times the derivative of cosine, which is negative sine of blop, and then times the derivative of the blop. And notice I would have positive k sine kx. But over here it was positive just sine kx, no k. That is why in the antiderivative you have to divide out a k. So I could divide out a k here, so I could divide out a k there, and then boom, it would be gone. And the derivative would be sine of kx. So because the derivative of cosine is negative sine, that's why the antiderivative of positive sine had to be negative cosine. Because if you take the derivative of negative cosine, you'd end up with positive sine. So keep that in mind. Okay, and then the same idea is at work here. Okay, notice the antiderivative of cosine is positive sine because the derivative of sine is positive cosine. So if I'm going backwards, taking the derivative, the antiderivative of cosine, I have positive sine. And then again, the k's are there in case you have a chain rule type situation. Okay, then with 5, 6, 7, and 8, all these are just the backwards formulas for the trig derivatives. The derivative of tangent is secant squared, so the antiderivative of secant squared is tangent. The derivative of negative cotangent is cosecant squared, so the antiderivative of cosecant squared is negative cotangent. And then so on and so forth. These are the same idea. So these are all the backwards formulas of the derivatives that we've learned before. Okay, so we're going to use all of this on the last page.